Hello everyone. Have you ever wondered how a CPU works? Probably not. Me neither. Although I have a couple of years experience in software development and programming, this question never really came to me. And actually, as a programmer, you don't really need to know how things work on an electronic level, because that's what compilers are essentially for. So in the last Christmas vacation I had some spare time, and finally this question came to me. How does a CPU actually work? So I did the reasonable thing and did some online research. I read some papers, watched some YouTube videos, and finally I stumbled across a video series from a guy named Ben Eater. What he did was he built a computer, or a CPU, an 8-bit CPU, on a breadboard. And while doing so, he explained every step and every component in great detail. So if any of you is interested in how a CPU works, I highly recommend his videos. They're really high quality videos and very educational. As I watched his videos, I was really fascinated. And also as I saw his breadboard computer finally working and flashing and doing things, I thought, man, this thing is awesome. I need one of those. And since you can't buy those things, if you want to have one, you have to build it yourself. And building things, or just getting your hands on things, is probably the best way to understand how they work. So that's what I did then. I just started building my own breadboard computer. And while doing so, I also thought, well, if I'm going to build one, I might as well improve the design a little bit. Because the computer that Ben Eater built was based on the SAP1 design, where SAP1 stands for simple as possible. And as simple as possible is just designed for educational purposes. But the computer that you have then is not all that powerful. For example, it only had 16 bytes of RAM, and the ALU only could perform addition and subtraction, but no logic or bit shift or anything like this. So that's where I improved the design of Ben Eater, or the SAP1. I have 16 bits of address space, which allows me to have up to 64 kilobytes of memory instead of 16 bytes. And within my 64K address space, I have 32K of actual RAM and 8K of ROM. And the ROM allows me to store programs or subroutines in a non-volatile memory, so that when I switch off the machine and turn it back on again, it's still there. One program, for example, would be a small bootloader, which just resets and initializes the machine. And as a last instruction, it just jumps to the first address in RAM. So the first major change I made while building this computer, I just significantly changed the bus layout. So in the SAP1 design, you only have a single 8-bit data bus, which is shared for everything, for addresses, for instructions, for data. And that can get somewhat congested. And if you are actually performing instructions, they will take a lot of cycles. I have two 8-bit buses that feed from my registers into the ALU called left and right bus. And also I have an additional bus which takes then the result from the ALU to wherever it is needed. So I have essentially three 8-bit data buses. And additionally, I have the 16-bit address bus, which is of course required to address any value in my 64K of memory. Another major improvement I did was I wanted to have more registers. So the SAP1 design only has an A and a B register. And that's not enough. So I have 4 general purpose registers. They're all exactly identical. And I also have some special purpose registers. So a temporary register is what I call it, or you could also call it memory data register, where I just temporarily store operands or a byte of an address. Another small but still significant improvement I made to the machine was I added a stack pointer. It's only an 8-bit stack pointer, but still, it's a stack pointer, which allows me to have 256 bytes of stack memory, which in turn allows me to have subroutines, for example, in my program. The last change, or major change, I applied to the design is I added more functionality to my ALU, mainly the logic operations AND, OR, and XOR, and also bit shift operations like left shift, right shift, rotate left, rotate right. And especially the last ones, they are really helpful if you want to, for example, perform multiplications and divisions. And these are the major changes I applied to the breadboard computer that Ben Eater built. And my plans for the near future would be to make a couple of short videos where I explain, first of all, where I got my design decisions from. I didn't make them all up by myself, to be honest. And also what they enable me to do with this CPU in contrast to the SAP1 CPU. This might be interesting for the occasional nerd out there. And so I hope to see you next time. Maybe.